Hi everybody, today we're looking at Euler's method, and it's a way by which we can use the differential equation of a curve to obtain an approximation of function values at a particular point. Now it's all based on the idea that a tangent line is very close to the values of the function around a point of contact. So this is sine x and my tangent line is at the origin there. And we can see that on either side close to the origin that the values of the tangent are very close to the function values. So from what we can look at, they look identical. Now we know that if we zoom in they wouldn't be identical, but it's enough to say that they're very close. Okay, so how do we actually work through it? Well, generally what you're given is you're given some derivative and you're given a starting point of the function. So in this case we're told that the function starts at the origin. Now this is not sine x, this is a different function which I'll talk about later. And all we know for the start is that the tangent line to the curve at the origin is horizontal. So the derivative here is 0. Now, based off of that, we're saying that this point is an approximation for the value of the function at 0.1. And we're saying it's a pretty good approximation because it's close to the point of contact. So this tangent line here, showing going along here, that's a tangent to the curve at x equals 0. So the derivative at x equals 0 must be 0 because it's a horizontal tangent. And we're saying that out here, just 0.1 to the right, well, that tangent line is still very close to the curve. And so then the value of the tangent line at 0.1 will be a good approximation for the value of the function at 0.1. Now after that, we then draw this next line, and the derivative at 0.1 gives us the slope of this line. So what we're saying then is that, so we calculate the derivative at 0.1 and we say, okay, that's roughly how the graph is increasing between 0.1 and 0.2. Now again, it's only an approximation of how the graph is increasing because it's a linear approximation, whereas the curve is probably increasing in a non-linear way. But again, it's all just based on approximations. So we say, well, this the derivative at 0.1 gives us a pretty good idea of how the graph is increasing between 0.1 and 0.2. So we calculate that increase, and then we can calculate the second point. So it's based on an approximation of the point at 0.1 and an approximation of the increase in the curve. So this is an approximation of the increase in f of x being the function that we're trying to get the values of, from 0.1 to 0.2. So how would we actually calculate this value? Well, it would be the value at 0.1, it would be the y value at 0.1. Now we call that y1, so that's the approximate value of f of 0.1, because it's after we've done one step of Euler's method. So Euler's method is this idea of drawing tangents and calculating the next point on. So it's y1 because it's the approximate value of f of 0.1 after one step of Euler's method. Now, if I was to get y2, which is this point here, so y2 is going to be y1 plus, now the slope of the tangent is given by the derivative at 0.1. So plus, so the slope f dash at 0.1 times by the difference between 0.1 and 0.2, which is 0.1. Or I'll be a bit more explicit, 0.2 take 0.1. So you might say, well, why? Like, why does that work? Well, if you think about f dash of 0.1, that's telling us the increase over a unit 1. So it tells us the increase over a whole unit of 1. Now here, we just want the increase over a unit of 0.1. So I take the increase of a unit over 1. So we could write this as f dash of is whatever the derivative is divided by 1. That's what the slope is. And then I times it by 0.1 on 0.1. And so f of dash of 0.1 times by 0.1 gives me the increase where the x step is 1, or 0.1 rather. So remember the idea is that's y step over x step. The original x step is a whole unit of 1. I only want an x step of 0.1, so I multiply top and bottom by 0.1 and it gives me the y step, or the increase, over an x step of 0.1. So that's y2. Now a similar thing would happen to get y3 after 3 steps. So first step, second step, now third step. So y3 would then be y2. My approximation for the function value at point 2 plus. Now it will be a new derivative. It will be the value of the derivative at point 2 because we're now using that to approximate the increase between point 2 and point 3. And again, I multiply it. My x step is 0.1, so I just multiply it by 0.1. And so this leads us to a general formula that y of n plus 1, the n plus 1 step, is going to be the previous y value, yn, plus the derivative, f dash of xn, whatever the previous x value was. Because you see, if you think about it, on our third step, the previous x value was 0.2. On our second step, our previous value was 0.1. And then we times it by h, which is a constant step value. So the step value won't change. So the increase in the x-coordinate going from one step to the next will always be the same. And then they've shown it here in a slightly different way. So yn plus h is our step value. And you'll notice that h is the increase in x. Because it's how we increase xn to get xn plus 1. Now the derivative, they express as f of xn yn. Now the main thing is derivative can be a function in x and y. So that's important to note. Okay, so how do we work through the numbers of this? Well, we're going to do it for dy dx equals 2x, which is the function above. And so the function we're trying to approximate is x squared. I think it's useful to start with a function that we can actually approximate to see how well it works. Now the zero step, now in all cases they'll give you a point on the original function. They'll tell you that the actual function has this point, and that's where you start. So I'm going to start at a point on x squared, which is 0, 0. And I'm going to try and approximate it at 0.5, the value of x squared at 0.5. Okay, so the value of the derivative at when x is 0 is just 0. So yn plus 1, y1 is going to be y0 plus the step value, we're doing 0.1, times by the value of the derivative, which is 0. So y0 is 0, so it's just 0 plus 0, which equals 0. So y1 is 0. Now, so then after step 1, we've got an x value of 0.1 and a y value of 0. So we read off the y value from the point in the previous column, the last column in the previous row rather. So the last column in the previous row gives us our y value for the next row. And that makes sense, that's what we found here. This is the point 0.1 in the x, 0 in the y. Okay, alright, now the value of the derivative when x is 0.1 is 2 times 0.1, which equals 0.2. y2 is therefore going to be y1 plus the step value times by the derivative, so 0.1 times 0.2, so that's 0 plus 0.02 to 0.02. So after 2 steps, we've now got an x value of 0.2 and a y value of 0.02. And if I go back up, x value here, 0.2, y value here, 0.02. So we can see that it's checking out. Now the value of the derivative at 0.2 is 0.4. So then y3 is y2 plus step value 0.1 times by the value of the derivative. So it's 0.02 plus 0.04, which is 0.06. So then after 3 steps, the x value is 0.3, the y value is 0.06. Let's just check that on the graph. X value 0.3, y value 0.06. Yep, that checks out. Okay, so we won't go back to the graph anymore, it's checking out. Now the value of the derivative at 0.3 is 2 times 0.3, which is 0.6. So then y4 is y3 plus the step value times by the derivative. Which is 0.12. Okay, now we're after 4 steps, our x value is 0.4, our y value is 0.12. The value of the derivative at 0.4 is 0.8. And then y5 is y4 plus 0.1 times 0.8. So it's 0.12 plus 0.08, which is 0.2. So after 5 steps, we've got an x value of 0.5 and a y value of 0.2. So what is that saying? Well, our approximation is for y equals x squared when x is 0.5. And note that it should be 0.5 squared, which is 0.25. So it's only out by 0.05, which isn't bad. It's not perfect, but it's an approximation. It's a reasonable approximation. So let's have a look at what's actually going on. So this is y equals x squared. And these are my approximations. So that's the first one, second one, third, fourth, and fifth. So yes, it's not awesome, but it's an approximation, and it's okay for an approximation. Now, you could say, well, hang on, you could get a better approximation. Let's say you made your step 0.05, because here the function value is close, the tangent is closer to the function value. And I'd have to say, yes, you could get a better approximation. And so what I've done is I've actually drawn, it's a little hard to see, but I've drawn dashed lines for these approximations. So we go 0.05, then we go up to 0.1, then we go on to 0.15, up to 0.12, up to 0.25, and you can see that those approximations are closer to the function than the approximations of 0.1. So this is the key point, that smaller step sizes improve your approximation, because you're not going as far along the tangent, because you see the further along the tangent you go, the further away from a curve you get, because the curve is curving while the tangent's staying straight. So if you take smaller step sizes, you're not going as far along your tangent, so you're staying closer to your function. So a smaller step size improves your approximation. Okay, so let's actually look at a past exam question. Now, I will confess that I have actually worked through this one, and that's because there's a lot of numbers and it's a lot of just calculations. But I encourage you to have your calculator here and actually do the maths with me. I'll just put the numbers in, but if you actually check it on the calculator, you'll be able to make sure that I haven't made a mistake. So we need our columns: step, xn, yn, dy dx, which is, if I rearrange that, it's minus 2 x take 1 times y. Rearrangement on that differential equation there. And then this is yn plus 1. Okay, alright, so step 0. So have they given us a starting point? Yes. When y is 2, x is 0. So the point 0, 2. We know that's on the actual original function. Everything else is going to be an approximation. And we've got a step value of 0.1. Okay, so first of all, we're going to calculate the derivative when x is 0 and y is 2. That'll be minus 2 times 0, take 1 times 2. So it'll be minus 1 times 2. So it'll be 2. So the slope of the tangent when x is 0 is 2. Okay, using that to get yn plus 1. So y1 will be y0 plus the step value times by the derivative, which is 2. y0 is 2, so it's 2 plus 0.2, which is 2.2. Okay. Now what are we actually approximating? We're approximating the maximum value of y, and that's actually given in a different section. We're told that it occurs when x equals 0.5. So I'm going to have to do this 5 times. Step 1. xn, okay, so that's when we've had an increase of a step value, so it's 0.1. y1 is 2.2, given in the last column of the previous row. Now the derivative, I'm using 0.1 and 2.2 to find the derivative, because that's my approximation for the point when x equals 0.1. So minus 2 times 0.1, take 1 times by 2.2, and I'm going to start relying on my notes here. It's 1.76, so y2 is equal to y1 plus the step value times by the derivative. y1 is 2.2 plus 0.176, and so that is 2.376. Okay, that's after the first step. Okay, second step. Now I'm at 0.2. yn is 2.376, so the value of the derivative is 2 times 0.2 take 1 times by 2.376, and this gives us a value of 1.4256. So then y3 will be y2, which is 2.376, plus the step value times by the derivative, which is 1.4256, which then comes to 2.51856. I'll talk about accuracy a little bit later. Okay, alright. Third step. Gets a bit tedious. Okay. So it's minus 2 times 0.3, take 1, times by 2.51856, giving me 1.007424. Y4 then is 2.51856 plus 0.1. Sorry, that back there, that should be 0.1. It's always consistent. It's always a step value. Times by 1.007424, giving me, and this is where I start rounding, 2.6193. So fourth step, x is 0.4, y is 2.6193. The value of the derivative is minus 2 times 0.4, take 1, times by 2.6193. Working that through and calculating it, it's 0.52386. So then y5 is y4 2.6193 plus the step 0.1 times by the derivative, and then that works out to be 2.67169. And then fifth step, x is 0.5, the value of y is 2.67, and that's what we're looking for. We're looking for the value when x is 0.5, and so we've found it. And so that's our answer. So the approximation for y when x is 2.67, rather x is 0.5, is 2.67. Okay, now how can each of the approximations, so we didn't find the approximation in B, so that's something else that we'll do later, but how can the approximation in C be made more accurate? Well, that's a smaller step size. That's pretty much a standard answer to any Euler's method problem. So let's have a look at the results in the mark scheme. So 6 marks, they're pretty much giving 1 for every y value. Their table is slightly different, but they're not going to knock you for a different table. Okay, they can't do that. And so I prefer my table method, but if you prefer the way the IB have set it out here, that's fine. Go with whatever you're comfortable with. Now, 2.67, I think you can appreciate that if you round any of your values too early, you're going to get something wildly different to 2.67. And notice that there's an accuracy mark for this number, meaning they're going to want you to get it. Now, in this case, we needed 2 decimal places to get 3 significant figures. So I'd suggest at least all your values should go to 4 decimal places. Okay? but the more decimal places you use, the safer you are. So I would say at a minimum go to 4 decimal places, but you could go to more if you wanted to. As I've been going for quite a while, and I just want to finish up by showing you how to do this on your calculator. So if you go across to recursion, now an plus 1 is what we'll do for x, so that will just be an. So I can just press the across button, and then I've got an plus 1. No, the step is 0.1, so that's how we get our new x values, by adding 0.1 each time. And bn is where we enter the recursion value for yn plus 1. So that will be, instead of y, it will be bn, and it will be bn plus the step value, 0.1, times by the derivative, and it's the value of the derivative where we're using xn and yn, or in this formula, an and bn. Now what was it? It was minus 2 times an, take 1, times by the value of bn. So really what I've done is I've replaced x with an and y with bn. Okay, now we've got to set up our table. So we want our table to start at 0 and to end at 0.5. And they're basically going to ask us, what's your first x value? And that was 0. What's your first y value? That was 2. And we don't need to set anything else. And so then we go to our table. Okay, so I've done something wrong. So must have been the way I set it up. So we're ending at 0.5. It's really not liking that. Now okay. So where it says end, that's not the x value, that's the number of steps. So we're saying we need it done for 5 steps to take us from 0 to 0.5. So let's try that. So end is number of steps, not x value. So we go back to the table, step 0, 1, 2, 3, 4, 5, 2.6716, pretty close to what we got, just certainly the same to 2 decimal places. Okay, and so that's how you can do it on your calculator. And if you ever had to do it on your calculator, what you'd do is you would just basically write that table down in your exam paper, because they'd want to see each of these bn plus 1 values, and so you just write down each of those, and that would give you your intermediate marks between your start and your end. Okay? Alright, so you're only going to do it by hand if you're in a paper 1. If you're in a paper 2 or 3, then you're going to use your calculator and you're going to write just all the intermediate values down until you get to the end.